In today's lesson, we're going to be going through section 5.4, exponential functions, differentiation, and integration. The function f of x is equal to ln of x is represented on a graph as consistently moving in the positive direction. Therefore, the inverse function is set equal to e of x, which is represented as consistently moving positive as well. Having the domain set is all real numbers, and having the range set as all positive real numbers. As we can see, it will never reach negative or key. And this can be further represented. The inverse relationship between these two functions, ln of x and e of x. For any real number, the function of the inverse function of x is equal to ln of the inverse function of x, which will then cancel out and simply be equal to x for any real number. If x is rational, then ln of e of x will be equal to x ln of e, which will then also be equal to x, as these two will cancel out. Because no matter what, the natural logarithmic function will always be 1-to-1 between the inverse and e of x, and we'll agree for all rational values of x. This can all be denoted in this form, referred to as the natural exponential function. And that is, if y is equal to e of x, then x is equal to ln of y. Another form we can see this is if ln of e of x is equal to x, and furthermore, e to the power of ln of x is equal to x. Using the problem presented in the slides, we are given 7 is equal to ex plus 1. To solve this, we would take the ln of both sides which will then result in ln of 7 equaling x plus 1. We can then move the 1 to the other side, simplifying 1, simplifying it into ln of 7 minus 1 is equal to x. This is how we'd solve for something along these lines. And you can simply plug this into the calculator and it will present us with a value 0.946 approximate. And you could always go back and check your answer by presenting 7 equal to E, plugging in this into x. So ln of 7 minus 1 plus 1. These will cancel out, these will cancel out, and all you're left with is 7. Some important rules to remember when using operations with exponential functions. If e to the power of a and e to the power of b is presented, it is the same as e a plus b, as well as e to the power of a divided by e to the power of b is equal to e to the a minus b. As we showed earlier, the graph of the function of e of x is presented as follows. Some properties that we can point out is that the domain reaches negative infinity, positive infinity. It is continuous, increasing, never decreasing. The graph is constantly concave upward on its entire domain. The limit of, as x approaches infinity, of e of x is both equal to 0 and infinity. As we can see that it never reaches 0 here, so that's how we represent it with the limit of 0, and it will constantly be going to infinity in the other direction. When finding the derivative of a function e to the power of x, we can see that the derivative of e to the x will always equal e to the x. We can also present this as the derivative of e to the u will be equal to e to the u times du dx. One simple example presented to us that we can use to be able to identify this is the derivative of e to the power of x minus 1 is equal to eu du dx. So when finding the derivative of this and still presented with e, the derivative will come out as 2 to the e to the power of x minus 1, showing that we're getting both the eu and the du, as this is the derivative of the function presented in its power. Inversely, we can show that the integral of e to the x dx is equal to e to the x plus c, as well as e to the u du is equal to e to the u plus c. As we've discussed before, they are 1-to-1. Using another simple example from the slide, we're presented with the integral of 3 to the x plus 1 dx. We can let u be equal to 3x plus 1, and to find du, it is equal to 3 dx. So then we would multiply and divide to present and introduce the missing factor of 3 into the integrand, so that now we can rewrite the integral is e to the 3x plus 1 du by removing this and replacing it. As we can see, equal to each other, as well as replacing this with u. And now that we're presented with eu du, we can simply write it back in. 1/3 eu du is the final integral plus c. And when plugging everything back in, we're presented with 1 divided by 3 e to the 3x plus 1 times 3 plus c. Simplified, we'll be presented with e 3x plus 1 divided by 3 plus c. One last problem that we can find ourselves presented with when finding areas bounded by exponential functions. We're presented with the definite integral 0 to 1 e to the negative x dx. This can be shown on the graph as this, because as we see, we're presented with the negative x. As we're searching for this area, we can come to the conclusion that the integral will be equal to negative e, the negative x, in the bound 0 to 1. So presented as e to the negative 1 minus negative 1, 1 minus 1 to the e, which approximates to 0.632, giving us our area for the given definite integral, as we're looking for areas bounded by exponential functions. With these basic concepts, we can use exponential functions to assist us with understanding and finding different functions.